Hello, everyone, and welcome to our open lecture number 3, 6G testbed and simulation happening today. I welcome the speakers and all the attendees. Thank you for joining. I will start with some general information regarding our event today. The session will be recorded and published on the 16G website. And you are welcome to post your questions and comments in the chat, and our speakers will do their best to address them during the meeting or after the meeting. And of course, you are encouraged to join the discussion online using our hashtags and tagging our Association 16G Global. And if you experience any technical issue, you can contact the host directly. I will move forward with the welcome and the introduction, and I will give the floor now to Ana Garcia Armada. She will be presenting testing waveforms, beamforms, and application for the next generation of mobile communications. Ana, you have the floor.
Thank you very much. Let me share my screen. It is a pleasure. Thank you for the invitation. And it is a pleasure to talk to you today about this exciting topic. At least it is nice for me, and also to share it with good friends and colleagues. So I would like to talk about why I think it is important to test waveforms, beamforming applications for the next generation of mobile communications. And I would like to give some examples of things we have been doing and we are doing now. So this, of course, is in the frame of the evolution, the constant evolution of wireless communications towards new systems. And at the moment, we have 5G that is already being deployed, and will in some years reach to its all these complete functionalities, giving birth to enhanced mobile broadband and also massive machine type communications and ultra reliable low latency. And of course, we are already thinking about adding a new dimension to 6G. This new dimension is probably going to be the digital world, where we will be able to coexist both in our human world, in the physical world of things, and in the digital world, and all this seamlessly through communications. And for the first time, I think we are also seeing that attention is paid to sustainability of our technologies and to achieving a global coverage, so trying to not leave anybody behind. These, of course, are new challenges, and new challenges call for new technologies. We should, as usual, as for every new generation, think about what are the best waveforms to achieve these requirements. We should think of what are the frequencies and always try to go to higher frequencies that will allow us to have the broad available bandwidth to be able to offer these services. And I believe we also need to find new degrees of freedom, because what we have now is being a bit exhaustive. We led MIMO to massive MIMO and cell-less MIMO, and it seems we cannot do beyond. And I think the key is adaptation and flexibility even further. And to do all this, to do new waveform frequencies, adaptation, degrees of freedom, we need realistic simulations and prototyping and measurements to be able to design, analyze new physical layer techniques. That is where I work, mostly in physical layer, to know if they are suitable, if they can support these new emerging applications, and to have some insights before we go and deploy and completely standardize them. So today I would like to give you 3 examples of how and why I think this is important, that are based on the experience of my research group. The first of them is frame on the evolution from 4G to 5G, so it's past work, but I think it's still quite important, because we will have face the same situation now going to 6G. It is about massive machine type communications, and here I would like to give some example of how to design new waveforms and to test them. Second example is frame on 5G. And it is about how to test the use of millimeter waves for enhanced mobile broadband. And then the third one is more futuristic, going towards 6G or even 7G, who knows. And it is a possibility to add new degrees of freedom with the use of liquid antennas. So I'm going to go to the first example. And this first example is about how to optimize multi-carrier waveforms for the use of machine type communications. So as I say, this is in a time frame where there was the need to define how to do and the extension of the broadband signals of OFDM, of LTE to machine type communications, and to be able to coexist small narrowband signals with broadband signals. It is important that these broadband signals don't interfere and allow an easy sharing of the spectrum, even at the side or even in the middle with this narrowband. So for this reason, OFDM is not good, because OFDM has a lot of interference in the adjacent channels, a lot of out-of-band emissions because of the sync spectrum. So as you probably know, at that time, there was a discussion, shall we use filter bank multi-carrier? Shall we use generalized frequency division multiplexing, universal frequency division multiplexing? So there were many waveforms that stem from traditional OFDM to try to accommodate this. And we thought maybe it was possible to just filter the OFDM. So our idea, and others' ideas also, right, was to, instead of having this big interference in the transition band, go to a filter that performs a more accurate filtering to avoid this out-of-band emissions. And of course, we did some simulation, right? So can we filter with different kinds of filter? How much can we gain with respect to the traditional OFDM? And are we able to accommodate a narrowband signal next to the OFDM? So based on this analysis and simulations, it seemed that this kind of filtering that we called mask OFDM, because we filter in the frequency domain, could be good. But one important question is, can this work in the real world? And can this be used with normal mobile phones, so they can work with the broadband signal, and at the same time they can leave space for the narrowband? So we decided to test this with open air interface, which is a particular software that matches well with simulation and implementation. And I'm going to show you a very quick video that shows a little bit how we did this. Let me put it a little bit low. So this is our setup. We have a conventional broadband signal that is going to be generated with, let me just maybe keep, yeah, like this. And the USRPs are implemented the narrowband signal. And we have a phone, the commercial phone, that is going to receive the broadband signal. And this is the narrowband signal. And the narrowband signal at the moment is doing very well because there is nothing else in the air, right? So it has a good constellation. But now we switch on the broadband LTE signal on the open air interface. And now it will appear next to the narrowband signal. And of course, it will interfere because it is very close. And that we can notice that the constellation is not as good, right? So anyway, at the same time, we have the mobile phone that is working with the broadband signal and without any problem. Now we change and we transmit a filtered OFDM in the broadband one. And now we will see that as soon as the new waveform arrives, the narrowband signal is slightly better. So the interference is lower, but we see that the phone works perfectly well. So this filtered OFDM can work with a commercial device without any problem, and at the same time, it can improve the performance of the narrowband. So this is an example that I think it is important, right? That we can see that what we are proposing, besides analytically looking good, it can really work. Second example is a project where we are, it's now, we are working on now, and we're about to finish. We are trying millimeter waves to provide also an application. Application is immersive music therapy based on virtual reality in a nursing home. And this project has several parts. One is to have a simulator to understand well what to do with millimeter waves, because they are not yet deployed, at least not in Spain. So we need to understand what numerology, what MCS, what beamforming. And of course, it's good to validate this simulator with measurements, but at the same time, we wanted to see how we really can take this new radio 5G with millimeter wave, this powerful tool, to be useful for in this case, for the elderly. So again, maybe.
Segovia, viva mi tierra, Segovia, viva Segovia, Segovia, viva mi tierra, por eso de Champú nos gusta vivir en ella, nos gusta vivir en ella, Segovia, viva mi tierra. Ya tenemos algo bueno en este pueblo, señores. Ya tenemos algo bueno. Buenos chicos, buenas chicas, trigo, cebada y centeno. Trigo, cebada y centeno, ya tenemos. A mi suegra le he metido la cabeza del retrete. A mi suegra le he metido la cabeza del retrete. Cuando se la saqué, tenía echada permanente.
Para unir alma con alma, corazón con corazón, reír contigo ante cualquier dolor, llorar contigo será tu salvación. Pero si tú meditas bien, lo dejo todo, que no se te haga tarde y te encuentres en la calle perdida.
So in this example, we see that, well, not only we use this technology to make people happy, which I think is a very important objective, but also we use it to validate our simulator and to provide a better understanding to the network operator and to the manufacturer of what are the capabilities of the equipment, the new equipment, to really do this immersive video therapy. So for example, here you see some course validating the simulator. So we have some measurements, we have our simulated values, and we can see that the difference between both is small. Then this allows us to also simulate environments that are different from the one that we were able to test, and extrapolate and look to the future and tell them maybe what you can improve in the current equipment. And the third example is looking more to the future. And we believe it is possible to reconfigure the channel by reconfiguring the antenna. And there is not much until now done in terms of changing the antenna. So instead of adapting to the channel, and if it is bad and there is a blockage, there is nothing you can do, we can add new degrees of freedom if the antenna can be completely reshaped in shape, right? But how to do this? Well, one idea is to build arrays of liquid antennas, because with liquid, you can completely adapt to any defined shape. And as I say, if there is a blockage, maybe you can move your antenna a little bit to a direction where the communication is not blocked. So we are looking at using again, which is an alloy of gallium and indium that is liquid. It's a metal that is liquid at room temperature. It's innocuous, so it can be used. But of course, here, again, the same question. Before, I mean, there is already some work, theoretical work of our group and many other groups. But we should also take a look at, is it possible? Is it possible to build antennas and to build arrays, not only antennas, and to build a whole communication system based on this idea, because if it is not feasible, then it's not worth to do any more theory, right? So we are doing some experiments in the lab, very initial. And you can see here in this short video that we have a column of this metal that as we change the size, we are changing the adaptation frequency of the antenna. And this, of course, can be done with pumps, but we would not like to have pumps in a mobile phone, right? So here I'm showing how we can move this liquid by using electromagnetic fields. So with a signal that controls the liquid, we can as well send information and change the position of the liquid or the shape of the antenna. Well, of course, this needs a lot of further work. We are just starting, but we believe it can be, the opportunities that it can open are very big, right? So just to conclude with these examples, I want to emphasize that we need to do simulations, we need to do prototyping in this way, in this challenging times of evolution of mobile communications. We cannot just rely on analysis, and we need to test and understand better how our channels behave, how our waveforms behave, and what are the possibilities simultaneously as the analytical work. And I show you these 3 examples, one of these machine type communications, the other related to millimeter waves for mobile broadband. And the third one that is, as I say, more a wish probably, that, but we are strongly working on that, to find another source of degrees of freedom that we believe could be in the antenna reconfigurability. And this is all. I would like to thank, of course, the projects and the colleagues that are working with me. And I will be very happy to answer any questions. I think I'm going to stop sharing so then I can see better the chat. But
thank you very much, Anna. It's Monique here. Apologies if before I missed the start, but I had some technical problems. So thanks to Valentin who took over the start. Anna, you covered several aspects here. I don't know if there are questions from the audience. I wanted to first of all have a look. I don't see questions, but please, guys, if you feel like you're having questions. Okay, there is Jörg that has one. I also have a couple, but Jörg, please go ahead with your question.
Hi, Anna. Yeah, just a quick question. For your second example, it wasn't quite clear to me. Was the VR part just sort of an example use case and you then simulated the traffic? Or actually those VR goggles were using wireless transmissions and you were really just sort of doing sort of communications experiments in that case?
Yes, we were doing the whole thing live. So we had a millimeter wave transmission that, you know, now in Spain, we still don't have the frequencies auctioned, but well, for experiments, you can apply for a special permission and it is allowed. So there is a setup in Segovia where we have the millimeter wave transmitting, and these elderly people were using the millimeter wave signal to do the immersive experience. And the simulation was just recreating the radio transmission just to validate the simulation, understand if we were accurately capturing the channel effects and all the numerology and everything. But in this case, the real world was supporting actually the development of the simulation. So now that the simulator is validated, we can use it for other environments that we cannot replicate in real life.
Excellent. Thanks a lot.
Thank you, Anna. Thank you, Jörg, for the question. Anna, I dropped a question here in the chat. So 6G adds new frequency bands, like high millimeters wave bands. So do you plan to extend your trial to that bands?
This particular trial, we don't, because we are using equipment from a manufacturer. And of course, we need, in these cases, we need to use whatever is available today, right? So for them, terahertz is going to come 10 years later in the roadmap. So what are we doing regarding higher frequencies? We are working on the waveforms, actually, because in my opinion, as far as we keep going further in frequency, we are going to need a signal that is that has less problems with the amplifier, right? So that is more constant envelope. So rather than these waveforms that I showed that are OFDM with filtering and whatever, with a little bit less out of band emissions, but still with high peak to average power ratio and difficult to amplify, we are working on versions of OFDM that are constant envelope. So there is already a proposal, it's called constant envelope or OFDM. There is literature already on that, and we are working on how to estimate the channel because it's not evident and things like that. But also we are proposing a new constant envelope form of OFDM that is going to have many advantages because it will also be good for highly varying channels, which is another challenge, right? So how to do everything at the same time? You want to be able to amplify, but at the same time, you want a signal that is robust to channel variations. There is the OTFS, but this has a very high peak to average ratio. So we are working still only on waveforms because, well, there is a long way to go until we reach to these higher frequencies. And we believe this good amplification, this constant envelope or close to constant envelope is a key feature. Of course, you can always argue, do we need still a multi-carrier waveform? Maybe we could go with a normal single carrier, but this possibility of OFDM, of multiplexing several users, of taking advantage of the multipath to create multi-user diversity, this is difficult to give up. And I still think there are ways to do waveforms that have all these possibilities, and we're working on that. So, but still not test-based with equipment. Sorry, not yet.
Thanks, Anna. Thanks a lot. One of the things that come up when thinking about conventional liquid antennas is that they rather slow down the tuning time because of their fluid nature. Is there any specific breakthrough or innovation with respect to what you presented us in that direction that you can share with us?
Yes, we are happy with this new idea of moving the liquid with an electromagnetic field, avoiding any mechanical systems, because mechanical systems always have a delay, right? Have a latency that is difficult. So in the lab, we managed to do this within milliseconds. And well, the channel coherence time is usually within milliseconds. I mean, if you go, of course, in a vehicle, it will be faster, but we are seeing that with these electromagnetic fields, we can cope with times, adaptation times, that can cope with normal applications coherence times. But this is an experiment. I mean, we still have a long way to go until we really get so we're moving the drop, but we're still not changing the shape with this electromagnetic field, but we believe this is the way. Having said that, we are reading literature about micropumps, and it seems they are evolving very fast. And maybe also there will be mechanical ways of adapting even as fast the liquid. But our belief is it's better to keep things in the electrical and electromagnetic control size. Also, this is easier also to control and adapt, but also faster. Yeah.
Thank you very much, Anna. So promising directions to be explored further. I think your presentation gives a lot of food for thoughts. I really liked also, the engagement of your videos in which you show the engagement of final end users of this technology. It's amazing, and actually it once again highlights the importance that the future communication networks will have also at the level of social inclusion and democratizations of digital access. So I would like with this to thank you, because we have now come to the end of your slots. I invite all the participants to keep contact with Anna and eventually to send her directly some questions. The slides will be made available, so there will be the opportunities to further interactions later on. Thank you. Muchas gracias.
Thank you very much. With pleasure. I will stay here so I can even communicate with the chat or whatever.
Thank you very much. Thank you. Dear ladies and gentlemen, now it's the time for the next slot, the next presentation from Jörg Widmer, that is a research professor at IMDEA Networks. And Jörg will focus on practical joint communications and sensing at millimeter wave frequencies. So I'm glad to give him the floor and listen to his presentation. We can see your slides, perfect. So please, Jörg, go ahead.
Excellent. Thanks a lot. So thanks a lot for inviting me. I'm very happy to talk a little bit about the work we're doing here. I know that the second lecture was on integrated communication and sensing. So here I'll not so much go into the sensing and like basically how to do the sensing, localization and communication part, but really the practical aspects. And a lot of the research we do in that area really is using prototypes, we build test beds and so on. So I guess since you already had the second lecture, you already saw all the use cases that are coming up more and more: smart factories, augmented virtual reality, like Anna just presented, autonomous vehicles, which have an enormous amount of sensors, but you could always use more sensing information. This is by no means a new topic. Using wireless for sensing has been going on for the past 2 decades. But now is a particularly interesting time because now communication systems have become so powerful in terms of the antennas, in terms of the bandwidth and the frequencies at which they operate, that now the accuracy is high enough that you can use joint communication and sensing in much more general settings. It works with high accuracy in many more scenarios, which starts to make it of practical use. Now here also, experimental research is extremely important. You can obviously like do a lot of analysis, simulate a lot, but in the end, whether it really works, whether you get a certain sensing accuracy, how well it interacts with ongoing communications, interference, and so on, you will only see in real testbeds and prototypes, just because the performance so critically depends on the specific channel environment that you're in, hardware imperfections, calibration, the synchronization you can achieve in practical settings between transmitter and receiver, and so on. So this is really something where to really assess the viability, practical experiments are extremely important. Now, one example, I'll look into it here. We're doing this, we're looking at sub-6 gigahertz and we're looking at millimeter wave. In this talk, I'll focus on millimeter wave, particularly because, well, on the one hand side, of course, this is extremely interesting now in the context of 5G and R at millimeter wave frequencies to achieve multi-gigabit data rates per user and very high levels of spatial reuse because of the very directional communication. But these exact same properties also make it very usable, very useful for accurate localization and sensing, right? So the larger the spectrum, the higher the time resolution that you have for the channel. And that's very important for accurate ranging. And the larger the antenna array, not in terms of size, but in terms of number of antenna elements, and the better your phase resolution, the better the angle resolution that you can achieve if you want to sort of do, for example, angle of arrival estimation for localization. And now here, what we were really interested in is the real world accuracy that you can achieve, especially with inexpensive off-the-shelf devices, because a lot of this sensing, of course, the research is done in the lab, but in the end, it should work on smartphones with millimeter wave chipsets, or your millimeter wave local area networks that in the future you may have at home. Now, designing testbeds or finding the right tools with which to do tests is always a hard problem. We started research there 6-7 years ago where it was much, much more of a problem. There were really no suitable millimeter wave devices out there. the first thing we did was trying to instrument off-the-shelf devices. And the picture you see here is one of the first millimeter wave consumer devices, the TP-Link Talon router, which implements 802.11ad, which is a wireless local area network protocol that operates at 60 gigahertz. And now this is, of course, a closed source device with a closed operating system that basically you can't use it for anything else other than data communication. We wanted to use it for research purposes. So we started hacking that device and specifically ported OpenWRT, which is an open source embedded Linux, to this device, which allows you then full access to the operating system. You can modify the whole protocol stack that sits on top of the interfaces. And we extended the 802.11ad wireless drivers themselves to be able to implement new functionality. For example, modifying the millimeter wave beam training, the beam forming vectors themselves to enable CSI extraction and so on. This was a lot of sort of really engineering work, just sort of poking in the binary firmware until you figure out what does what, and was sort of quite an involved process. But in the end, we were able to enable quite a lot of functionality. And one thing we then used this for is to build a fully passive millimeter wave angle-based location system. Now, at millimeter wave frequencies, specifically for those very simple consumer devices, angle estimation works a little bit different than in the usual MIMO case. Specifically, you have only one RF chain that's connected to a phased array, right? So you have a lot of antenna elements, each connected to a phase shifter, but those are all connected just to a single RF chain, right? So you always only see the channel through that whole array response, but you cannot do individual phase estimation of your signal at any of the antenna elements, which would be needed for conventional algorithms like music. Now, of course, there are many ways of, even with such a very simple transceiver, to estimate angles of arrival and angles of departure. One very simple way that we implemented, but like I said, I mean, there's a lot of different ways of doing that, is the following. These devices, the antenna arrays, they generate sort of beam patterns, and they're not very perfect, right? I mean, there you see really, this is not lab grade hardware. This is sort of cheap. These are cheap consumer devices. The beam patterns you see here in blue, right? And they're not very beautiful, but okay, they do have a main lobe, they do have some side lobes, and obviously higher gain in the main lobe direction. Now, one simple way that can be implemented on this consumer device is the following. It does beam training anyway, which means it tests different beam patterns and records signal strength. Now, you can use this for sparse angle of arrival estimation. Basically, the question you're asking is, if I see a certain pattern of SNRs, right? So here, for example, the first sector that's probed is sector 12, and there's very low gain in that direction. And the direction of arrival is the red bar. And then I probe sector 16 and I see a very high gain. And then I probe sector 63 and I see some intermediate gain, right? So what you're basically asking is, if I know the shapes of the beam patterns and I see a certain sequence of SNR values, what's the most likely angle of arrival that caused this sequence? And clearly, if you test a lot of patterns, right, then this becomes a very well-determined optimization problem. If you only have few patterns, it's harder. But that's one way how you can actually do angle of arrival estimation with this very cheap hardware. And with this, you can build a location system. Now, I'm not going to go too much into the details of what we built here. What we actually wanted to do in this first incarnation is the following. These devices did not do ranging. Even though you can implement very accurate ranging with millimeter wave, these devices did not support it, simply because the firmware did not enable that. So what we wanted to build is a purely angle-based location system. Now, if you know the positions of your of an anchor point, right? Then angle-based localization is trivial. It's just triangulation, right? You have two anchors, you know the angles to those anchors, and where those lines intersect, that's where your that's where your terminal is. So that's trivial. But in realistic settings, very often, for example, for an indoor deployment, you might not have a map of where all the access points are located. And of course, also, you don't just have line of sight, you also have reflections from walls. Ideally, you would also like to have the whole floor plan and so on. So the question we asked is, can you build a millimeter wave location system if all you have is angles or angle differences, and you don't know any anchor point locations, you don't know where the walls are. And it turns out that's actually it's highly non-trivial, but it's actually solvable if you have user mobility over time. Because then sort of you can map the angle changes to possible positions, and of course the access points themselves don't change in their location, and that actually becomes sort of a highly complex sort of higher order trigonometric polynomial, but you can actually solve such a system. And then what you get is a location system that over time not just locates the access points, right? So this is an indoor scenario. The red squares and crosses are sort of actual access point positions and estimated positions, and they're quite accurate. We have a certain user trajectory, which is in green, together with the estimated positions. But what we also get from the multipath components over time are where reflections are coming from. And those are the black crosses that you see here, mostly on the walls, but some of them are also sort of in the middle of the room. Now, this happens because the system doesn't know anything, right? It doesn't know where the walls are at the beginning, and it needs to first figure out where the access points are and so on and so on. So those lines here that are misplaced actually come from the fact that the system sees a second order reflection, but it doesn't know where the wall is. It doesn't know that it's a second order reflection. So it assumes it's a first order reflection and places the wall there. But now, as you move more and more on the right-hand side, actually, you can figure out that there is another wall. So this reflection must have come from somewhere else. It is actually a second order reflection. And you can, over time, then resolve these ambiguities, right? And place the wall where it actually is located. And of course, what you can also do is then, once you've figured out where the walls are, where the access points are, and where the user device is, you can use this again for network control. For example, here what we did is a scenario where we have seven access points deployed at the walls of a very large room. We have dividing walls in between. And we have a very mean trajectory for the user device, right? So the user device moves around those obstacle walls and then sees an access point, loses connectivity with that access point because it disappears behind the wall and then reappears and so on. So this is a really challenging scenario for handover. And typically, well, the typical approach for this would be you just probe whichever direction works and configure your antenna accordingly. But that also means while you're probing, you're losing connectivity or you're losing your link. And if you know the whole scenario, if you know where the walls are, of course, you can also predict your movement and predict when you're likely going to disappear behind a wall and do your handover to the most suitable access point beforehand. And this basically shows the throughput on the right-hand side at the bottom between this location-based approach where you get much more stable, much higher throughput than a standard approach that just relies on beam training. When the link goes bad, you train again, you find a new access point, goes bad again, and so on. So this is something where even with very simple devices, you can already achieve quite a lot. Now, okay, I see there's a question. I'll take this one right now from Joseph. If we have implemented all the components or this is in cooperation with partners, actually, so this previous work with the firmware hacking, that was in cooperation with partners. We worked together with TU Darmstadt in Germany and the University of Brescia in Italy. And those two groups are extremely good at firmware hacking. And just because this is such a hard problem to actually open up those devices, figure out which bit in the firmware is responsible for which functionality, This was done in conjunction with those two groups to spread the load a little bit and advance more quickly. Now, we extended this work further. This was sort of the very first device was sort of basically just what was available 5-6 years ago. Hardware has become a bit more capable. And what the photo that's shown here are actually newer millimeter wave devices with much better antenna arrays. And you see here a picture of that array. It's a planar array with 6x6 elements, so 36 antenna elements in total, which gives you very nice, very narrow beams. And on that hardware, also what we were able to do is enable ranging. So this FTM is actually fine time measurement. It's standardized in 811AD. And we were able to get that functionality to work. It's not supported out of the box with those devices. They're not designed for this. But we actually managed to find a firmware that we could hack and enable that functionality. And we were quite surprised about the accuracy you can achieve with these very cheap consumer devices. So under ideal settings in a lab with sort of like not too complex multipaths, but it's not an anechoic chamber, right? It's still sort of a lab setting with furniture and everything. The angle accuracy that we got for the line of sight path was around 1 degree. And the ranging error that we got with these very cheap devices under line of sight was about 10 centimeters, right? So whereas before you needed like very complex filtering mechanisms and like many access points and then sort of integrate the measurements and so on to achieve like decimeter level accuracy at sub 6 gigahertz, right? Here, a single device supports that out of the box, unmodified, which is quite surprising. Now, on the other hand, of course, the downside is it just gives you a very accurate path, whichever that may be. If it's the line of sight path, great. You can use the line of sight path for very accurate localization. But if it's a reflection, you don't know that this is a reflection because, well, the line of sight path is not present. So your estimated location points towards the wall, but not towards where the object actually is. So one big problem we had with such systems was that you can't easily tell whether it's line of sight or non-line of sight. If it's line of sight, you have extremely high accuracy. If it's non-line of sight, you're very far off. Now, here actually, sub 6 gigahertz can help. Not to merge information, because millimeter wave is typically way more accurate than sub 6 gigahertz, but to distinguish line of sight paths from not line of sight paths. So basically to tell when should we use the millimeter wave measurement because it's line of sight, or when should we use the sub 6 gigahertz measurement because the millimeter wave one is completely off because it's non-line of sight. And this works because often you have obstructed line of sight at sub 6 gigahertz, where sort of you have an obstacle that blocks the line of sight path and it's opaque at millimeter wave, but it's transparent at sub 6 gigahertz. And you have this obstructed line of sight component that you can identify because it's very short, right? It's the shortest distance is always sort of the line of sight or obstructed line of sight one. And then we were able to build a location system out of this. And interestingly, this very good ranging accuracy that you get under ideal conditions, we were able to more or less maintain that even in complex settings with a lot of non-line of sight for millimeter wave, even for relatively sparse deployments and so on. So again, I'm not going to go into all the details, but in a large complex settings with multiple rooms and access points not in every room. So those are sort of multi-band access points with millimeter wave and a sub 6 gigahertz interface. The median location error we achieved was still 10 centimeters with a dense deployment and 20 centimeters with a sparse deployment, where you only have 2 access points in 2 large lecture rooms, and in all the offices where we also do measurements and it's non-line of sight, you have no access points. Still, the accuracy is like 20 centimeters. So that's really remarkable. Now, one step further, Of course, there's a lot of work where you can no longer work with off-the-shelf devices, right? So you can do a lot, you can hack them, you can extract CSI, but if you really want to work at the signal processing level, off-the-shelf devices do not provide that access. And so for work that goes in that direction, where we need much deeper access, we built a platform for millimeter wave and sub-6 gigahertz research based on Xilinx FPGAs. They're very powerful FPGAs that allow to sort of do both millimeter wave as well as sub-6 gigahertz experimentation. This is a platform that's open source available. So we published this, we made the implementation available. You can just buy the components and build such a system yourself. It's a memory-based design to speed up prototyping, which basically means you have 4 gigabytes of RAM on those boards integrated. And you can just sort of generate your waveform in MATLAB, upload it to the board, transmit it over the air via antennas, and then receive it at the other end, ship it back into MATLAB and process it there, right? So that's something where for rapid prototyping, playing around with different waveforms, that's extremely useful. And now here also, we designed the system to allow a lot of flexibility in how you configure it. You can freely configure the frequency at which it operates and the bandwidth with which it operates. And of course, because of the memory-based design, you can freely choose the waveform that's being transmitted, while at the same time being much more powerful in terms of what you can do from the real-time perspective and working with longer traces than you could do, for example, with an oscilloscope. And so here we have 3 basic modes of operation, up to 8x8 MIMO at any sub-6 gigahertz frequency, up to 4x4 MIMO at millimeter wave frequencies, with up to 2 gigahertz per channel, which gives 8 gigahertz in total, which is extremely powerful for such a system. Or you can even have mixed configurations, which is the photo that's shown here, where you have 2x2 MIMO and 4x4 millimeter wave running at the same time with common baseband from the same board, which is quite nice for 5G and R experimentation. Now, what we did with this is microdoppler estimation in a joint communication and sensing system. And just very, very briefly, what that system actually does is, so what we want to do is activity recognition, person tracking in indoor settings with multiple persons. So on the one hand side, we track where multipath reflections are coming from, how the multipath environment is changing, and use that to track where persons are. And then from the multipath components that are reflected off of a person, we do microdoppler extraction. And one example of such a microdoppler spectrum over time is shown in this blue plot. What is microdoppler? It's basically the Doppler signal that's reflected off of an object that has multiple components, right? So the normal Doppler would be you're walking towards an access point, the signal is reflected back from your chest, right? And that gives a certain Doppler frequency, a certain frequency shift. Now, at the same time, your arms and your legs are also swinging and moving back and forth with different speeds relative to your body. And that gives microdoppler, like Doppler modulations on top of the main Doppler frequency. And one example here is this walking example. And you can see the torso in yellow, that's the main Doppler component. And then you have lighter components on top from the limbs. And now doing this with a radar waveform is relatively straightforward. That's been done for a long time. But we wanted to implement this for just the normal data communication system where this is much harder. And so we actually implemented this. Turns out it works quite well on that hardware. That's one example where you can no longer work with off-the-shelf devices, but you actually need sort of, full FPGA-based software-defined radios. And we're currently extending this towards a real-time 5G, 6G experimentation platform. So there are a few platforms out there, Open Air Interface, SIS-RAN are some sort of open source examples. Our platform has the advantage that it's targeting the sort of very high-end range of the spectrum, right? So very wide channels, very high order MIMO. And of course, then also for joint communication and sensing research, that's going to be very interesting. Now, there are a lot of open research problems. Robustness for these joint communication cases is something that's still very much of an open issue. Those systems are typically designed for communication, and you have slightly different requirements if you want to use them for sensing. So calibration is a very big issue. And to conclude, let me just get to the end to leave a little bit of time for questions as well. So joint communication and sensing is one of the areas where experimentation is really critical. It's not a new topic, like I mentioned before. Wireless location systems, for example, have been around for a long, long time, but it's very timely now and of very practical relevance because it plays such a big role in the applications that are foreseen for 6G. With that, let me conclude and thank you very much. And I'd be happy to receive any questions.
Thank you, Jörg. Again, another very dense presentation full of insights and also direction for further thinking. So again, I invite you, so here I see a question in the audience from Joseph. Jörg, does your team have implemented all components, or have you been cooperating with other partners?
Yeah, I briefly answered that already before, but yeah, just to repeat, for the firmware hacking parts, working with off-the-shelf devices, we actually work together with two other teams who are very good at firmware hacking. Like one team at the University of Brescia in Italy and another team at TU Darmstadt in Germany. The FPGA-based systems we designed ourselves. So there we have a few people with a lot of FPGA, software-defined radio expertise, and basically those are fully developed in-house.
Thank you, Jörg. Now I just drop you another question here. Well, that's common to other, I guess, research projects and presentations we might see today. Real prototypes are rather complex and expensive to build. How to solve this challenge, especially if many devices have to be considered in the proof of concept for integrated communication and sensing, especially because a lot of these technologies are still in an early stage of their, use.
Absolutely right, and that's a tough question. There's no magical solution, obviously. Now we're at the point where this is not so expensive anymore, and of course, not so expensive is very relative. But for example, these software-defined radios that we build our system, our software-defined radio system on for the microdoppler extraction. They cost like 12,000 euros, which is not that much, right? So there, building a 4 or 5 node testbed is expensive, but it's feasible. For a lot of the work that requires more dense deployments, that's another very strong reason why we experiment with these off-the-shelf devices. For example, the ones that I showed before, we have 2 deployments with more than 30 nodes, right? And those are normal consumer routers, right? They cost $200. So they're building a 30-node testbed is no problem at all. And of course, then it very much depends on how deep do you need the access, right? If it's really something where you want to design the waveform and experiment with OTFS instead of OFDM, then of course, yeah, you have to go for the more expensive software-defined radio option. But actually, I mean, what we found the more we worked with it is you can, with a bit of firmware hacking, you can actually do a lot with off-the-shelf devices, and then of course build large test beds with those.
So that's a good perspective on the future of many researchers and innovation initiatives. Thanks a lot. There is another question here I see. Basically it's asking to elaborate a little bit on what open source platform means to you within the context of your project, and how possibly everyone could build upon what you just described, your platform essentially.
Mm-hmm. So here we work in different modes of operation. So on the one hand side, it's open source in the sense that the documentation is out there, the software is out there. If you just want to read our paper, buy the hardware, download the software, and build the system yourself, you can do that. And then it's in your lab, you can do with it whatever you want. We've done that in a number of cases, and then we also worked with the partners to actually help them. I mean, it's still quite a bit of, it's still non-trivial, right? So then to work with a few other universities and labs in Europe and the US to actually build a copy of our system there. That's one mode of operation. Then the other mode is, of course, like a lot of the expertise, how to really work with the system is with us, and building that up takes a while. Working with such radios is always high effort. And then we've partnered with others where basically we jointly did some work where we designed whatever, a new location system, but then we actually experimented with it in the setup that we already had here, where sort of then fast prototyping and implementing some new idea was much, much quicker to do it here than to do it with them replicating their test bed. And we've done both, right, to write joint papers, and both works. You're still muted, Monique.
Thank you, Jörg. We're getting to the end of this slot. I don't see any question for the time being, but I saw before, after Anna concluded, there were some further questions. So I'm sure that our audience might have some more comments or points. Is there any measurement on terahertz channel in a real environment? It seems not clear how much difference the simulated terahertz channel in literature is from the real one. Can you comment on this, and then we conclude your intervention?
Mm-hmm. So there is, we are not yet doing terahertz measurements because we don't have the hardware yet. That's still like an order of magnitude more expensive. But we are collaborating with Josep Jornet from Northeastern University, who has a lot of very good practical research on millimeter wave. And actually, that's a very nice combination because he's got the hardware, the terahertz transceivers. We have the software-defined radio that's extremely flexible and can also be made to work with the terahertz devices that he has. And so at the moment, that's one thing we're doing. We're building sort of a joint test bed together with him to do joint experiments for terahertz. And now from the papers, I guess, or in terms of what the channel looks like, I guess I would refer to his papers because he's really the expert there. But I think the actual channel still varies quite a bit compared to the simulated ones, right? In terms of, for example, one thing that was interesting to see was the ranges you can achieve, right? It does work over tens of meters with very, very low gain, but it still does work, right? The multipath that you see. So from these practical measurements, actually, we got a lot of very interesting insights that confirmed or refuted some of the assumptions that were made in those simulation papers.
Thank you very much, Jörg. I would like then to invite all participants to this lecture to keep in touch with Jörg and follow up on discussions directly with him. Jörg, thanks a lot once again. And now I would like to give the floor to our next speakers, that is Josep Eichinger. Is the 16G Working Group 4 chair, and is from Huawei Technologies in Düsseldorf, and is gonna give us a lecture about paving the way towards 6G testbed. Joseph, the floor is yours. Thanks a lot. We cannot hear you, Joseph, you're muted.
Yes, now I'm...
okay, fine.
You
perfect.
can hear me and see me, that's good. Yes, thank you for the introduction, and yes, I'm working for Huawei in Munich, actually, and we have here also a research department and a lab, and I'm also happy to be the 16G chair for the Working Group 4 and responsible for testing and evaluation, and in this role, I had some, let's say, I got some experiences and some feedback from the members of 16G, what we could do and what are the pain points and what are the problems. And that is also was a motivation for me to build the slide set, what I will show now step by step. How to build test beds. And if we saw now from two different presentations, two different test beds, actually much more because Jörg has shown not only one. But it's a challenge, it's not easy. And what we learned from the old days, let's say with 5G test beds, and we are still in the 5G time, that the verticals, and this is maybe important to understand better, the verticals has been addressed in 5G first. In LTE, it was a bit, but in 5G, it has been addressed more. This will also continue in 6G, and that means in 6G, maybe more and more functions will be added to satisfy the needs of the verticals. Whatever verticals means, it's a very broad term. At the end, verticals, most of the verticals, and I have a lot of experiences with industries and also with some health projects, verticals are not so much happier and to study standardization documents and to look what is written in and finally to find out what is implemented and what they can use. They would prefer to have some proof of concept first and then to classify or to sort out what is useful and what is not useful. Even now in the 5G time, different industries trying to understand what 5G can bring for them. And this many years after we have already released the first 5G standard, release 15 and 16, later on more designed for URLC. 5G-AA and 5G-ACA are some of the examples of this kind of organization trying to find out what can they do with 5G. And now we're talking about 6G. And in 6G, the complexity will increase, that's for sure. Maybe the complexity, let's say, at least if we talk about the services and the features what 6G bring, hopefully we can manage to reduce the complexity with respect to functionality, to hardware, whatever, as much as possible. But from the features that we see clearly, and you see it on the left side here, maybe I can switch on my pointer, then it can also point to the things. You see, we have not only 3 dots in the graph here, like in 5G, we have only 3, MBB, MTC, and URLC, also shown in previous slides. This is the setup of 5G. Now, let's go to 6G. We come to a native AI. You have already seen the open lecture. You can watch the recorded video here. We have integrated satellite system. We have new frequency bands. We talked about terahertz and millimeter wave in this call. We have sustainability as a very big point, also addressed in the first presentation. Extreme connectivity, much more as today. And I don't want to say last but not least, and very important, network sensing, what also has addressed. That means we see already the spectrum of functions increase. But how can we get confidence that the new technologies, what we invent, the new functions, what we design and propose, are really helpful for our future users? Future users are not academics. Future users are not vendors of equipment. Future users are either you and me, or a factory owner, or a hospital operator, or maybe I don't know, a smart city operator. These are the final user, and I was really happy to see this first talk that they have already involved this kind of care units to do some tests with end users. The proposed path to the future, at least in my opinion, is to start with proof of concept, with real world trials as soon as possible, together with all kinds of stakeholders. That is what my belief is, what we have to push forward and what should be different to the 5G time. Usually, and that was already done to some extent in the last years, usually you have the first phase, you show only use cases. The focus is to show the vision of the next generation, what they could do, to demonstrate some use cases more from the, let's say, how it looks like perspective. It's sometimes a feasibility demo, but not in detail. It's only a high-level feasibility demo. It should not be limited to RAN features. I also want to point out to the higher protocol levels, to the architecture and what we see in 6G, also AI levels. In the past, many of the experiments has been focused more on radio functions, maybe protocols, and how to work with sub 6 gigahertz bands and whatever, how to get a URLC feature running. Most of this kind of demos are really very simplified, and as I said, maybe focus on a layer 1 or layer 2, or then it stops. It's still necessary for many new use cases. We are not at the end here, because if you look to the 1.6G white paper where we have already use cases listed, or if you look to the ITUR, at the moment working on understanding which kind of use cases are important for 6G. And if you study the other literatures, you see a lot of interesting use cases. This is what we already do. So that means company 1, institute 1, they do some experiments, and maybe also you on limited scope, but it's okay. But the next step should be to study the feasibility of key functions. We see here a lot of vertical industries in the slide here, just addressed by some pictograms here. And the focus in this phase is mainly on key technologies like sensing, like maybe coverage, what can we get with terahertz, how much distance can we get with some data rate. All other functions are more or less simplified or ignored. The main driver of this are ICT companies and, sorry, also academia. I forgot to add this because of the research task, what they have to do. Verticals are not much involved most of the time here, and I just want to challenge us a bit in order to say we are living in a kind of ICT bubble here, where we believe we understand what are the real requirements, we understand what are the real needs and pain points of the vertical industry. I know from my history it's not true. Very small scale demos because we have missing know-how. Sometimes we don't know. Let's say if you are not expert in radio, you cannot do experiments with radio. If you are not expert in AI, how can you do something with AI? That means we have different expertise in different, let's say, part of the universities and industries. And for sure, limited resources. Jörg said the terahertz tests and demonstrator are really very expensive. That is where we are right now with 6G. To some extent, we are between phase 1 and phase 2. Now, how to solve this problem? If we have, on the one side, maybe in some areas, not enough know-how, or we have not enough money to get something running with very specific functionalities. And the question is, at the end, and also Jörg has a bit addressed this, trying to find out who has implemented a certain function. Maybe function for sensing, for imaging, for protocol design, for distributed AI at the UE or at the base station or network side. If you know who has something, and then you like radio guys, we are always looking for the higher layer functions because we are not extremely, let's say, deeply understanding this, and the same is maybe for the protocol guys on the NAS level. They don't have so much ideas about the real radio problems. And the same is also that we have more or less, in all cases here, less feedback from the verticals. And my proposal is here in this phase 3, where we go step by step now. We have to look for partners. 6G is going to support much more functionalities than 5G. And here's a list of a small list, and we have to look who can help in one of the functions to build a bigger, more convincing demonstrator, because at the end, the demonstrators, real life demonstrator, is the only one that show user truth. Simulations are necessary, but not the reality sometimes. And phase 4, I propose here, and that is what we could do in 1.6G or maybe also in different organizations. We should think about how to build a trusted simulation platform first. And because this is a baseline to understand how a certain algorithm or certain function is really running and can be interact with other parts of the 6G network. And the 6G network is much more than just value. One example would be to take NS3, many people have it, and maybe also ONNet, and to look around which partner has NS3 capabilities, NS3 functions or ONNet functions, and how can we connect both together over the internet, because we don't need strong real-time here, maybe internet is fine. And then we can perform more complex simulations. We could even connect this to a digital twin simulation tool. Here, as just an example, VBots, to model maybe the behavior of the industrial scenario or V2X scenarios in this kind of this digital twin tool. And then we can connect this to the NS3 or ONNet system in order to get to take this mobility model from the digital twin into account in the network simulations. The second part is to get maybe more functions from the hardware side, not just from the software side. I propose here that we should maybe in this time and 6G time think about to build a trusted marketplace for research and trials. A marketplace for functions, but also a marketplace for data. Function means here software, but also hardware functions, even simulation functions. This would lower the effort for verticals to cooperate, because they have, most of the time, I don't talk about the big giants like Siemens and some others, I talk about medium-sized enterprises. They don't have the power to build all of the things, but they still want to do experiments. And this kind of marketplace could be a possibility for them to cooperate easily in projects, because they can utilize some of the functions what we have already built here in different organizations here. The same is for data. I know many AI-based training data is already available for free, but this could be extended to different other data, not just AI-based training data. We can also store radio measurement data from core network, from the topical level, or from the sensing. We can give it to the partners in public or maybe in this in 1.6G. Also, log files for debugging are sometimes interested, and includes some valuable data what could be used later on for training and for research. But how to start? I have here a small testbed. We have shown this in UCAP 2022. It's somehow based on industrial scenario. It shows the different robots. It works with different robots. They interact with each other, like in a typical industrial environment where you have multiple processes working and depending on each other, also from the timing. And then we have key functionalities like what we have shown here, sensing. So terahertz enabled non-destructive quality control here. This is prototype antennas, and we have looked into the box and figured out what is inside. Here we need also for this kind of prototype post-processing. And post-processing, not all of the radio experts are famous in post-processing and imaging. That means you need also some partnering, maybe partners that can help you to analyze the data what you have recorded with all of the sensing equipment. So that is what we did here in my department here, but this is just an example here. And if you want to go further in the future, if you want to do it in a more general, not just for this example, then we could, and I propose this simply, maybe in my role as working group 4 chair, it's obvious. 16G could be a platform that hosts the 6G trial and verification platform, as a simulation, but also hardware prototyping or software prototyping. And this would be a good common platform where all partners can come together and do some joint tests or trustful working together. It's a big, we have a big member base already with academia, vendors, end users, take operators. My last number was 80, but maybe it has already increased to more. That means we have already in 16G 80 members and from 25 different countries. That's a very good, let's say, resource. And if you want to utilize this and you are not already in 16G, please look to the 16g.org webpage and check whether you would like to become a member here. And with this, as I said, we have the opportunity to bring together the expertise of industrial guys with digital twins, expertise of AI experts that can help to implement, I don't say simulate, implement, because we talk about testbeds, AI algorithms to use most enhanced AI functions and maybe also AI functions already pre-selected in the industry, not just in academia. We could use expertise in infrastructure sensing, also radio measurement tools, because many data can only be derived if you have good measurement interfaces and good way how to derive data from the systems. Moving trajectory, if you have robots in place, how is this robot moving fast, slow? What is the safety distance? What you have to consider if you have cobots where you interwork with humans here, and so on and so on. And also, last but not least, this imaging experts where helping to analyze our data.
Joseph, sorry, yeah. We're coming to the end of your slot. If we can wrap up so that we leave. Oh, perfect timing.
yes, I'm always I try to be in time, and this is the last slide. Thank you for your time, and I hope it inspires you to work together and in different projects.
Thank you, Joseph. Indeed, I think it's very important to have set this context. So all the participants to the call, all the audience is kindly invited to join possibly 16G for further work in this context. There is one question which I picked up from the audience that says, which vertical domain do you expect to be the first to adopt simultaneous communication and sensing in 6G? So do you think there's any vertical that is more prone to this transition?
Unfortunately, I have no glass ball here with me. I cannot look into, also no teacup with some tea. It's really difficult to answer these questions. We saw in 5G times that the car industry was jumping on the 5G train first. Then in the second level, the industry came. But they are still on the way and have not really made business with this one. My thinking is that due to the sensing feature, what we have, sensing plus AI, I'm quite sure that maybe automation at all sort of can be, let's say, the key vertical. What I don't like so much is to separate the verticals in this automotive verticals into the industrial verticals, farming verticals, because at the end they have a common need. If you have mobile devices in farming, in logistics, on the street, they're mobile devices, they're robot on wheels, more or less intelligent. If you have sensing needs in factories, in farms, in food production, maybe in car production, it's the same. Maybe we should look in 6G to have this kind of cross-border proposal here, where we find solutions and not domains.
Okay. Thanks a lot, Joseph. I again kindly invite our participants to the call to be in touch with Joseph for any further question. Thanks a lot. Now let's introduce the next speaker. I saw that Sandra is already online. She's with us. Sandra Lagen, Senior Researcher at CTTC. And today Sandra will talk about towards NS3G6G LENA, in particular focusing on evolving research and simulation through open source collaborative and developments. So Sandra, the floor is yours. Thanks a lot.
Thank you, Monique. Do you see my presentation? Yeah, I hope so. No? Yes,
okay. Perfect. Thank you.
Okay, so thank you very much, first of all, for inviting to this tutorial. In this talk, I will briefly introduce our research unit at CTTC that it's called Open Simulation and why we think that the open source simulation is very important to evolve in the research and the development. And I will provide an overview of the 5G LENA network simulators that it's one of the key assets that we design, develop, and maintain in our group. And then which are the ways we see that we are currently working on evolving the simulator towards the 5G advanced and 6G simulators that will come in the future. So I will talk about some of the topics we are currently working. So in our group, we strongly believe that the collaborative research has to be done through open source code developments. And we think that the technology development and indeed the standardization, what is more important, the standardization should be based on common software platforms and joint effort from both the community in the industry, in the academia, and all the partners to progress further, because otherwise what happens currently in the standardization, for example, is that every company has a different simulator and it's very difficult to reproduce and compare results. So we think that it would be good to have a common software platform. We do that in our group and we base our research here on NS3, that it's an open source end-to-end network simulator. Joseph already mentioned it also, and in particular, inside NS3, there are different modules, and we take care of the LENA and 5G LENA modules. We do releases in open source continuously with our recent developments and the recent findings. And also we have a strong commitment with the NS3 community. So we belong to the NS3 Executive Consortium, and we are maintainers of the LTE and NR, that is the LENA and 5G LENA modules. In our group, we have different research lines, and one of the lines is about the coexistence between 3GPP and IEEE, because one of the benefits of NS3 is that we have available also many versions of Wi-Fi, so of the IEEE amendments. So it's easy, and NS3 provides the interfaces to study coexistence of different technologies in the same wireless channel. Also, we have a very strong work on the modeling of the radio access network, both modeling of the different layers, including new algorithms, testing new architectures, and also we have expertise on the radio resource management and self-organized networks, and especially moving into this line of the disaggregated radio access networks that I will present later. Our methodological approach is that whatever we develop, we see how to integrate this in NS3, and then we design the models, develop them, validate, calibrate, and do evaluations in the 5G LENA module. So this is our website. In this website, so the repo that we develop is public. So you can, through the website, if you go to get the software, you can access to the repository. Also, we have a discussion group in a Google group. And you can, in this web, you can also access to the documentation. We have a PDF with the documentation, also the Oxygen documentation that is generated from the code, and papers where you can refer to, and etc. We have, until this year, we were tracking how many users were requesting access. Now the code is fully public. I will talk about this later. So we don't track anymore who is downloading it, but until this year, we had more than 1,000 users that requested access, including top telecom industry players. So this is a bit the history of the 5G LENA simulator, and I like to talk because this is the part from the LENA simulator for 4G. So as we want to see how we will evolve towards 6G, I think that looking at the history, it's also important. So the development of the LENA simulator for 4G started in 2010. and was thanks to collaboration with Ubiquisys, that it's now part of Cisco. And then the first release of the LENA code was in 2011. This code evolved, and there were different variants, including the operation in unlicensed bands like the LTE-U and the LTE license-assisted access, also an extension for device-to-device communications. All this in line and working towards the 4G advance, when carrier aggregation, for example, was included in the module. And it was later in the 2017 that we started the modeling of the NR thanks to a collaboration with Interdigital. We started with that, and we did the first release in the 2019. That is when we considered that the first release of the 5G. It was aligned with the release 15 of 3GPP specifications. And then we are doing continuous releases of different versions. And also we have different branches or extensions of the simulator for specific use cases, like, for example, the case of NRU, so new radio operating on unlicensed bands, or the case of NR-V2X, so NR specific, modified to enable the communication between vehicles and the vehicle-to-vehicle direct communication without going through the GNOT. It's important that in all this evolution, we need to keep a continuous track of the standard and to be aligned as much as possible with the new standard specifications. All this development of 5G LENA is thanks to collaborations we have with the industry, and we think it's very important to collaborate closely, in close consultation with the industry, because they know very close the standard. So, and this is how we benefit among all of us in the development of these simulators. For regards to the 5G LENA, we started with Interdigital, as I said. So thanks to that, we did the first release of the 5G LENA module, and also we work on the NRU module. It's the extension for the unlicensed operation, and we did many coexistence studies of NRU and Wi-Fi working at millimeter wave bands. We also had another collaboration with the Lawrence Livermore National Lab from the US about to build a spectrum sharing simulator in which we had LTE and NR coexisting in the same bands. Thanks to a grant from the National Institute of Standard Technology, we also developed the NR-V2X module focused on communication between vehicles using the Mode 2 resource allocation strategy. We will see, so that basically the users autonomously select the resources to transmit to other users in the neighborhood. Recently, we had a collaboration also with Huawei, in which we started to incorporate and to see how this disaggregated RAN architecture envisioned in the Open RAN framework, how this limited capacity front haul, mid haul, how all this architecture impacts on the end-to-end performance of the radio access network. Also, recently, we had a collaboration with Meta and about extending the simulator and doing improvements towards extended reality use cases. And we are about to start a project funded by the Spanish government that it's about all this Open RAN-like architecture, having disaggregated RAN functions and disaggregated distributed machine learning decision processes. So this is an end-to-end overview of the simulator. So we simulate everything from the remote host, the core network, going through the GNOT-B, the wireless channel, and the user. And this is for a single link, but as you can imagine, and you can see here in the deployment, we can simulate many cells, many GNOT-Bs, and many users. For example, in this deployment here, we have more than 1,000 users and around 100 GNOT-Bs. So what is very important for the simulations in NS3 is to allow these large-scale simulations, so to have simplified models and abstraction models so that we are able to simulate in close to real time, because I cannot say sometimes in real time, but close to real time, these complex networks. So the simulator now is available, is flexible to work from the 400 megahertz to 100 gigahertz, because we follow the 3GPP special channel model defined in 38901 for NR. So all this range in carrier frequencies can be used. We have tested the frequency range 1 and frequency range 2, and also NRU in the 60 gigahertz bands. But yeah, and we expect that in the future also new channel modeling for above 100 gigahertz will be defined and then incorporated in the simulator. We have a non-standalone architecture, so we have 5G in the radio access network, and especially in the physical and MAC layers. But for the core network, we still rely on the 4G EPC. The spatial channel model, as I said, this is was a big addition, but it also complicates the computational time because we have uniform planar arrays that can be composed of many antennas, and the channel modeling, it's getting complex as the more antennas are there, the more users, the more G0Bs, etc. We are working also on a simplified channel model to avoid this that is currently the bottleneck in some of the simulations, and this will be released also soon. Related to MAC and PHY layers, these are what we support. So we support of DMA, TDMA, a dynamic scheduled access, different schedulers, different hard methods. And we have also the support for multiple component carriers or bandwidth pairs, so to enable the carrier aggregation, time division multiplexing of numerologies. At the PHY, we support different numerologies, more than one. We have many, but more could be included and tested also. We support TDD and FDD. We have LDPC as per the standard. Well, we have an abstraction model of the physical layer that has been developed to be aligned with the LDPC coding, including also the 3GPP code block segmentation, the LDPC base graph selection, and valid for 2 MCS tables defined in NR. In NR there were 3, so we support MCS table 1 and table 2 that includes up to the 256 QAM. We recently also included the uplink power control and dual polarized MIMO. So we use MIMO by exploiting the diversity of dual polarized antennas, and we also included the rank adaptation in which we can switch from 1 to 2 streams dynamically. For the NRU extension, the big improvement here was the inclusion of listen before talk. So we have a channel access manager that controls when the NRU device can access to the channel, and it needs to apply a clear channel assessment procedure. We have different ways of doing the LBT and also implemented the energy detection to detect whether there is somebody in the channel or not. For the NRB2X extension, as I said, we focused on the broadcast communication, so the user transmitting to all the users in the neighborhood and using the out of coverage scenario. So basically users transmit without being in the coverage of the G0B, and for that they follow the mode to resource allocation. Basically the users autonomously select the resources to transmit on, and for that they can use a sensing based approach or a random selection. And what we have currently is a semi-persistent scheduling, so they do sensing or a random selection, and then this is persistently scheduled over time. So some recent developments examples that we have done. So here we have the NRU device. The main change here was the inclusion of the channel access manager to control the accesses, so the transmissions into the wireless channel. For the NRB2X simulation, here we have, for example, this was simulating a highway with 3 roads, and we can see there is a platoon of many vehicles that are moving, in this case, at the same speed, and then they intend to communicate with the others. Recently, we implemented many different traffic models according to NGMN and 3GPP specifications for gaming, VoIP, video, FTP, HTTP. We have also augmented reality, virtual reality, and cloud gaming applications. And all this is to support the XR and 5G advanced scenarios in the future. Also, we developed a tool that was available for LENA, and now it's available also for 5G LENA, that is the radio environmental map. That is a tool useful to see how it's your deployment, which is the SANR of your deployment, and to see that if in your simulation you have properly configured everything. And this has helped us to calibrate the simulator in terms of the SANR, as we can see here in the bottom figure, compared to the results by the 3GPP. The company is contributing to 3GPP. So how we intend to evolve towards the 6G LENA. So I will talk more what we see towards this 5G advanced simulator, and it's are things that we are currently working in collaboration with different companies or other entities. So one thing that we are working in the simulator is about the quality of service management, specialized for the case of mixed XR applications. So what happens in XR application is that a single user can generate various streams, for example, for video, audio data, even post control, and how we manage all these different streams through the web protocol stack is something that we are handling, how we can do a multi-layer quality of service management, because we can apply the quality of service management at the UPF, so at the core network. As we can see in this, we can apply different mapping functions. So mapping all the streams of the same UE to the same data radio beater, or having a specialized data radio beaters. So we can also have the MAC scheduler that applies quality of service policies. So all these, we are applying the quality of service in the whole protocol stack and seeing the interactions among all of them. And also another thing that we are studying, and that it's very interesting, is how to derive XR loopback mechanisms. So basically how, based on the evaluation of the, so we do simulations, and how, based on the KPIs that we get, for example, the packet error or the delay, how we can adjust the codec rate, or the rate of the video stream, for example, in these XR applications. Another thing we are working on in this 6G Blur project is about this disaggregated RAN architecture. So we envision, well, as Open RAN has defined, and 3GPP is also on the way, is to have different functions of the RAN access network to be distributed between different logical nodes placed at the radio unit, the distributed unit, and the centralized unit. These different nodes are in turn connected through mid-haul and front-haul links. So it's important to characterize all this architecture and see the impact of these different transport links on the end-to-end performance. So we are distributing the processing and the intelligence and everything. So it's very important also in all this architecture to derive end-to-end orchestration mechanisms to orchestrate both the RAN and also the transport. This includes what we have started working on, the front-haul compression techniques, because there is, when we do a split inside the feed, so the split that is considered, for example, in the Open RAN, splits the physical layer between the radio unit and the distributed unit. So there is a large amount of data that needs to go through these front-haul links, and this front-haul can be shared also between different radio units. So we need to see how to handle all these peaks of data through the front-haul. And also we envision that we will have different computing and controller entities distributed through the network. So we need to see how it is, well, we will have different controllers taking autonomous decisions. So how we control everything and how they take their own decisions, this needs to be handled and evaluated. So this is the idea of the project and what we intend to simulate also in 5G LENA in the near future, and also including the end-to-end resource management and management while controlling all these different controllers or edge computing resources that can operate in real time, non-real time, and can take decisions from the policy definition and up to the scheduling decisions. So we need to handle all this. Other work that we are working on, it's based on, well, that is well related to the UAB networks. We want to make the system able to detect attacks, so UAVs that can jam your communication. So for that, we have been developing the air-to-ground channel models and trying to incorporate machine learning decision to improve the security in these UAV networks. Another work we have been working is on the integration of 5G and time-sensitive networking for the Industry 4.0 scenarios. So we tried to evaluate if 5G was able to support time-critical services, and for that we derived flexible scheduling mechanisms for this ultra-reliable and low-latency communications in the Industry 4.0 scenarios. So on the way to follow, so in 5G simulation, still we need work to do. So we did a lot of work on the PHY and MAC layers and the different extensions, but RLC and above layers are still, we are still using the ones of LENA. So there is work to maybe configure in some cases or extend those layers to the NR specifications. Also, we miss the 5G core network. We are also working on a full MIMO model. So currently we support beamforming and the dual polarized MIMO, but not the full MIMO model with more than 2 streams. So this is some work we are now going to do. And also we are working, this was in the framework of Google Summer of Code. As I said, the 3GPP spatial channel model is very accurate, and especially for frequency range 2 is needed to have many arrays and many clusters modeling the propagation, but it's very complex for the system level simulators. No? So we have been working in a Google Summer of Code project in a simplified channel model that it can be valid for frequency range 1 and high frequency bands, but that it's much less complex and then more useful for large scale simulations. Related to the 5G advanced simulators, so as I said, we are already working on the extra enhancement, the quality of service management, and we expect to work also on the inclusion of artificial intelligence or machine learning techniques that are able to control or configure parts of the air interface. Also on the sidelink evolution, the evolution of the V2X, the evolution of the MIMO, the handset dynamic spectrum access, also the support for the UAV communications, and also the non-terrestrial improvements to be mixed with the terrestrial communications, and also maybe in the future also to see if we are able to support not only TDD, FDD, but also full duplex or XDD operations. Once the 6G standard is defined, of course, we would include the channel modeling for above 100 gigahertz, the modeling of the RAN, the different layers. We have to, as Anna was presenting, all this modulation, we need to see which is the one selected for 6G and then properly simulate that in the end-to-end simulators, in the system level simulators. And also what is more important, so one of the key parts that we need to develop is the phi abstraction model. So once the 6G is defined, we can work on the abstraction of the physical layer. So how to simulate this in less time, and likely we may need to consider this radio unit, the central distributed unit entities, so where the physical layer is split, and then we may need to have a two-layer physical abstraction model, no? Where part of the abstraction runs in the radio unit and the other part runs in the distributed unit. And also we need to incorporate all this decentralized RAN architecture that I already presented. Is the idea that we are going to do, but maybe for 6G, another architecture is envisioned. So yeah, towards this 6G LENA, recently we have adopted a new development strategy, and this is, I would like to briefly talk about this. And the thing is that there are many new features and new things to be developed towards the 5G advance or the 6G. And we know that many researchers and companies are already using the 5G LENA, and they are already implementing them, but it's somehow rare the cases that they contribute back to the 5G LENA. There's people that they do, but there are others that they do their own development. So the objective at what we want is that we want to make the life easier to all these companies and researchers so that they can contribute to the 5G LENA simulator. Because we think that this collaborative development would accelerate the way towards the 6G simulator. So, and more importantly, of course, the more users, companies that use the simulator, the more testing, validations, and calibrations that we will have. So how we do that is that since this year we have fully open, so 5G LENA is in open access so that anyone can access it. Up to now, the people needed to ask for permission, and we were giving the permission, but now you can access without permission, and anybody can create merge requests, so can contribute to our public NR repo. Our idea is to do more often releases so that all the companies and researchers can easily upgrade their code and stay up to date with the latest code, so that this is easier for the new contributions to come. And also we have a new release strategy that is each 5G LENA release is linked to a specific NS3 release. Previously, we were aligned with the master branch of NS3 and this was creating some problems for some of the users. So finally, each release is linked to a specific NS3 release. And our idea is also, of course, to give more technical tutorials and with examples of how to start with 5G LENA and all the NS3 simulators. These are our team here, and also PhD students that came to CTTC to do extensions on the simulator, and thanks to which we are evolving in this simulator. So thank you very much. If you have any question.
Thank you, Sandra. Thanks a lot. Again, a very dense presentation. I guess we could go on for much longer than 20 minutes with each of the speakers we had today, but thanks a lot. So here I see a question that Valentin posted. You have mentioned TSN implementation in Lena. Have you implemented TSN in all domains of the simulator? Have you done simulations with real wired TSN equipment, interoperability test?
No. So we just, this was a work that we did with a PhD student that came to see how the 5G could replace all the cables on all the TS. So if it could permit the time sensitive networking or this kind of time critical services. But we have not implemented TSN in NS3. We just try to look if 5G could replace and could be integrated with it, but the integration was not done well with TSN implemented in NS3. No, it was just the 5G adapted for the industrial use cases, but what we implemented in NS3 was just the 5G part adaptation but not TSN.
Thank you, Sandra. I just posted another question that was from the audience. Is physical process included in the simulator, including channel coding, modulation, decoding, demodulation?
Okay, yeah, this is a good question. Yeah, so this is a network simulator. What we do for the physical layer is to derive an abstraction model. And this abstraction model is basically a model that maps a certain SINR of the channel into a probability of error of a code block or a transport block. To derive these mapping curves are basically curves of the Blair block error rate with respect to the SINR for different modulation coding schemes, for different transport block sizes, for different LDPC base graph codes. To extract these curves, we did simulations in a link level simulator, simulating everything. But once we obtain these curves, what we have in NS3 is this abstraction model to make the simulations faster. Okay, so there are two works. One is to do with link level simulators. We develop this phi abstraction model, and then we include this simplified modeling of the physical layer into the simulator. So for 6G, for example, once the 6G, the physical layer is defined, what we will have to do is to have available some link level simulator of the physical layer, do simulations with that, and derive this physical abstraction layer that is like a simplified modeling that is faster to run, basically, to be included in the system level simulator. Because otherwise, in system level simulators, if you need to simulate all the physical layer, what you say, channel coding model, this is unfeasible. If you want to simulate many G-Node Bs, many users, it turns out to be unfeasible in terms of simulation time.
Okay, thanks, Sandra. So I would like to call also the other two speakers. I see Joseph has the camera on, maybe Jörg and Anna quickly for a last word on the lecture today. So we have heard from our four great speakers quite a lot of things about ongoing work towards 6G testbed experimental validation and simulation. I think we are in an early phase, but it's never too early to start in a way. So if you, I would like that you summarize a little bit what you think is the main message you would like to leave to the audience in one sentence quickly before I then conclude with a couple of information about future activities at the 1.6G level. So I would start with Anna, then go on with Jörg, Joseph, and Sandra. Just a quick wrap up on your side.
Yeah, thank you, Monique. Yeah, I think also it was clear from the questions from the attendees that going to higher frequencies is still a mystery of how these things are going to behave. And it is particularly important to be able to do some measurements, prototypes, and then simulations to understand how this can perform, and then be able to design the waveforms, the algorithms, even the routing or whatever. That would be that is, I mean, my message is that I think it is even more important today than ever to rely on these test beds and simulations.
Sure, feasibility check is absolutely a precondition here. Absolutely. Thanks, Anna. Jörg?
Yep, and just to follow on to that, I think this is getting even harder now that we are moving sort of, well, towards 6G and even higher frequencies, right? So millimeter wave, yes, there's still a lot of work to be done, but at least sort of there's hardware out there, right? You can buy millimeter wave equipment now. For a long time you couldn't, but by now sort of at least there are options. It's still a lot of work, right? I mean, it took us 3 years to build the system that we now have, right? So and that's also why a bit what Joseph said, right? It makes it's so important to work together, to not like everybody builds their own prototype, right? Reuse what's out there, work together with others, just because the effort is so high. And it's hard to publish just like the fact that you built a prototype. You've got to do research with it, right? So the years you put into it, that's just to get started. But what I wanted to say is basically sort of now that we're moving to terahertz frequencies or sub-terahertz frequencies, right? All of this becomes even harder, right? There you don't even have good hardware, right? You like, let alone finding like fully integrated transceivers, right? It's like people are still working on antennas and like trying to get them to work well enough, amplifiers and so on, right? This is incredibly hard. So there it becomes even much more important, right, to pool efforts, just because it's such a hard endeavor to really sort of build communication systems at these frequencies and then be able to use them.
Thank you, Jörg. Again, I think the main point is really to be aware that in this early investigation phase, it's simulation. It's even more important because we have to deal with a context in which a lot of equipments, a lot of components are not yet even available at prototype stage for early experimentation. So even more important, the kind of efforts you guys have been discussing and presenting today. Joseph, what is your view on this discussion to wrap up?
I fully agree to all of the previous speakers, and what I would like to add that as end users, in my view, is a missing piece of the puzzle, because we are not designing something for ourselves. We do something that our customer later on can make business. Customer has different meanings, but this is important, and therefore we have to recognize what he really needs, not just designing terahertz radio just because it's interesting. You have to find a reason for this. And this is for me a bit missing at the moment, and we are just looking how somebody else can make money out of our technology.
Okay, so a very important point that for all technologies must be very clear. We have also to meet the demand side, and we have to make sure that in doing our work, we clearly see what is the picture, what are the main core needs of our society and our technology and our economy when developing our technology. I think that's very important. Thank you, Joseph, for this. Sandra?
Yeah, no, I agree with all of them. I think networks are becoming every time more complex, not only with more frequency bands, but also reconfigurability in different layers, addressing different use cases, and for each of which we need to reconfigure and adapt this 5G or the future 6G. So all these various cases, so I think simulations and prototyping are, of course, needed to decide which is the best option for each case or which is the one to be adopted in the standard. So basically, yeah. And our view, as I said in my presentation, is that we should all work in a common platform to test everything under the same umbrella. But well, I think it's difficult, but it would be good to take a decision based on
Thank you, Sandra. I think that's very much important to take care of the complexity. It's clear that the more the future communication networks see the convergence of various other domains and technologies, from AI to edge to ultra reliable networks and so on and so forth, the scenario will get more complex, and it will be a challenge for all of the researchers and innovators to come up with powerful times to tackle this. So thanks a lot. It was amazing. I could spend much longer time to listen to all of you. Luckily, we will have the possibility to publish the slides if you all agree on the 1CG Association website. What I wanted to say before concluding this session is to quickly remind the fact that we have planned, so let me share, sorry, I wanted to share with you a couple of slides. So share, does it work? Yes, now it should work. I hope you can see. Can you see the slide?
Yes.
Okay, great. So first of all, this was one of the lectures that the 1CG organization has been organizing. There are 2 more in the pipeline that will come within the next few months. We had planned to have one in October, the next one in December, but maybe there will be some shift forward. So please stay tuned on the 1CG channels because more information about the next lecture will come up. A lot of opportunities to learn and also to look forward to the new research and innovation directions. But very important for all the community gathered around 6G research, regulation, innovation is the 1CG Summit that will take place on the 10th of November. So please save the dates. Very soon you will receive more details, more information about the agenda, the registration, all the modalities. The focus will be really on defining a path to intelligent and sustainable global 6G. We will have a lot of top experts from various domains, and the idea will really be to animate discussions and have interactive sessions so that everyone can also voice and raise their effort. For me, what is left to say, thanks a lot. Thanks a lot to all of you, the ones that have been listening, the ones that have been talking, and the ones that have been, of course, helping to organize this event. I'm looking forward to next opportunities to meet and discuss with you. Again, big thanks to Anna, Jörg, Joseph, and Sandra. And see you soon on these channels. Thanks a lot.